In this screencast, I'm going to talk about a phenomenon known as multicollinearity, and in particular, it's an important consideration when you are putting together polynomial regression models. So we've looked at several different types of regression models. Recall the general linear regression model in matrix form is shown here, y equals x beta plus epsilon, and it can be used to fit any relationship that is linear in the unknown parameters beta. That's what defines a linear regression model, is it's linear in beta. An example of a polynomial regression model is shown here. This is second degree and one variable, and it's linear in beta. This parameter epsilon represents the random errors that are associated with the measurements. We can also have a second degree polynomial in two variables, and this too is linear in beta. So we've got our linear terms and our quadratic, our second order terms, and we've also got an interaction term here at the end, x1 times x2. So these both are examples of polynomial models. Now let's talk about this phenomenon known as multicollinearity. Multicollinearity is a serious problem with polynomial models. It is obvious that x squared, x cubed, all the way up to xk are going to be highly correlated since they all depend upon x. And when you've got regressor variables that are highly correlated, then this can lead to something known as multicollinearity. The exact reason for this is beyond the scope of this class, but just keep in mind that it can be a serious problem with polynomial models. A common technique to mitigate the effects of multicollinearity is to standardize the x values. This also has the benefit of avoiding numerical problems associated with higher powers of x, and I'll kind of go through this here in a minute. But we can standardize where we have xi prime that represents our standardized x value. It's similar to how you've standardized variables when you convert x bar to z when we're talking about the standard normal distribution. So we take each x value, subtract the mean of x, and divide by the standard deviation of x. So let's go through an example here. We're going to create a fifth order polynomial, and I'll explain how we can standardize. Our x value is pressure in psi. Our weight fraction of hexane is the response. So let me show you what happens if we create a normal polynomial model out of these data. So here I have my powers. These are going to be powers that we're going to raise x to. I'm just going to go ahead and name this vector x. And I'm going to type in here equals x raised to the power above it. And Control-Shift-Enter, or Enter if you have a new version of Excel. And now I can just drag this over. And you see that when we have a high pressure, 1600, and we have a fifth order polynomial, we're getting really big numbers here. 1 times 10 to the 16th. On the lower side of our values, we have 200. So our data here, our X matrix, is going to have a huge range. And that's something we want to minimize. We want to standardize to eliminate multicollinearity, but also to put all of these regressor variables on the same playing field. So instead of doing that, let's go ahead and first calculate some statistics. We can calculate the average of x. I'm going to go ahead and name this x bar. We can calculate the standard deviation of x. Let's go ahead and name that s. And now what I want to do is I want to standardize instead. So let's delete those numbers. This I can just calculate as equal to x minus x bar divided by s. So those are our standardized variables. I'm going to go ahead and name this x std for standard. And then I can type in here x std raised to the power above it. And now since I wrote that as a relative formula, I can drag that over. And as a result, all of our parameters here are sort of between approximately -6 and +6. And so this makes it a lot easier to work with. The computations are not involving really small numbers and really big numbers. And also, this tends to eliminate or decrease multicollinearity of polynomial models. So now our model is going to be a model of our standardized variable, and that's important. I'm going to go ahead and use the regression tool. Our y input range is going to be the weight fraction of hexane. The x input range is going to be all of our polynomial regressors. I'm going to put this in a new worksheet. Go ahead and click OK. I can resize this, and we can take a look at our coefficients. you notice that the p-values of all of these coefficients are small, which means that each of these coefficients is significant in the model. If I go over here, I've plotted the data, and we can go ahead and take our predictions right here. I'm going to go ahead and control copy. I can go over to this chart and I just click in there, control paste. I can go ahead and format that. And what we end up with is our model that fits our data quite nicely. So our model becomes the following. We have a fifth order polynomial. I've just taken those coefficients from the regression output and put them into our model. Now, if you wanted to use this to predict the weight fraction of hexane for a future measurement, then you would have to standardize first. So you would take your pressure, subtract 900 because 900 is the average. That's x bar. Remember, we made that transformation. And 490 is our standard deviation. And then you could put this into the model. So it's most convenient to use two steps, convert pressure to x, and then you can use this equation up here to compute y. Alternatively, you could substitute this x into the model and solve for in terms of p. And this kind of takes some time, but this is definitely another option. You always want to analyze residuals. So if we took the residuals are shown here in the regression output. And if we plotted them, if we made a probability plot of those residuals, we can determine if the model is adequate. It looks like the p-value of that AD statistic is greater than 0.05, which is good. It's about 0.621, meaning that the residuals are normally distributed. We can also look at the residuals as a function of predicted weight fraction. This does look okay. There is some concern about non-constant variance. It looks like the variance increases and then gets smaller, but we've got such a limited number of samples here, it's really hard to determine if that's the case. So hopefully you learned a little bit more about polynomial models and multicollinearity in this screencast. Thanks for watching.